All right, so this is part 3 of the 4C.1 videos where we start talking about some of the parts of the graphs of rational functions. We haven't actually graphed any of the function yet. We've really only been talking about where the function can't be. So the function can't be where there is a vertical asymptote. It I don't want to say can't, but should not be where there is a horizontal asymptote. And the last type of place where the function does not exist is called a hole in the function. Holes in rational functions happen when the original function had something that would cause a divide by zero error, but once you simplified it, that thing canceled out. So it wasn't there in the simplified form, but in the original form of the function, it was there. So we still have to deal with that divide by zero error, and we just deal with it in a slightly different way. To identify holes, any polynomial that's canceled out. When we are simplifying at the very beginning of this process, we factor the top, we factor the bottom, the numerator and the denominator, and any of those factors that cancel out that have a variable in them, we're going to set that equal to 0 and solve the equation that we get. And that will give us the x value of the hole. And once we get that x value, we plug that x value into that reduced form of the rational function to get the y value. And now we've got an xy pair, and we plot it on the graph with a circle. Pretty easy, right? So here's holes. Unfortunately, when I was looking at examples 1 through 6 in your guided notes, I noticed that nothing canceled out in number 1, so there's no hole. In number 2, again, nothing canceled out, so no holes. In number 3, I think you're beginning to get the point. Nothing canceled out, no holes. I had to add some extra examples just so I could get some holes. There's no holes in number 4, and no holes in number 5, and no holes in number 6. So in the examples in the guided notes, no holes. I can't show you how to do it, so we're going to have to look at those extra examples that I added earlier. So extra example number 1. So in this case, the x plus 2 actually canceled out. So that's great. It canceled out. I know that I have a hole, right? Now, what has happened here is x plus 2 equals 0 would yield a negative 2 divide by zero error in the original function. So if I use this thing that canceled out in my final form, there's no divide by zero error. But if I plug that negative 2 into the original function in for x, I would end up with a divide by zero error. So to deal with this problem that arises, we create a hole in the graph. And in order to find that hole, again, we take that canceled out thing and set it equal to 0 and solve for x. I get x equals negative 2. I'm going to plug that negative 2 into the reduced form of the function. So remember, when we reduced it, we ended up here with x plus 1 over x minus 3. Well, for x, I plugged in negative 2, the x value of the whole, to get negative 1 over negative 5 when I reduce the fraction. Well, negative divided by negative is positive, so that's going to be positive 1/5. So the whole is going to be at negative 2, comma, 1/5. All right, well, so let's put the hole in the graph. We're going to go to negative 2, loop, loop. And 1/5 is it's not very far up from the x-axis. It's 1/5 of the way. So I put literally a circle on the graph right there, right above the x-axis for 1 over 5. 1/5 is about the same thing as 0.2. So it's, pretty close to the x-axis in this case, right? And that hole is going to be in my final function. When we finally get to graphing these things, we would end up sending our graph through the holes. And we'll make sure that the hole stays there in the graph, that it's identified and we see it. All right, let's look at another example. In this extra example number 2, and this time x minus 5 canceled out. So yay, something canceled out. That means that I have a hole. In the original function, if I used 5 for x, 5 minus 5 is 0, I would have a problem. In my final form, don't have that problem. So it's still a problem. It's still an issue. So we set it equal to 0, and I get x equals 5, and I plug that into the reduced form of the function, x plus 3. So instead of x, I use a 5. I couldn't plug it into the original starting function because then I would have a divide by 0 error. So I got to use the reduced form. Well, in this case, 5 plus 3 is 8. So that means on my graph at 5, comma 8, I'm going to have a hole in the graph. And literally, you just draw a small circle there. So right 5, up 8. We're about right here, and I'm just going to draw a circle. And when I start sketching my function, it might touch the edges of the circle, but that circle is going to stay there to represent the hole in the graph. It's going to let everyone know that there's a hole there. Well, that's it for holes. I mean, they're pretty easy to do. I mean, sometimes you have to do a little bit of math depending on what the final form of the rational function is. So you might have to do a little calculation. But you've got calculators for that, and it'll help you out. The idea is that vertical asymptotes and holes both would cause divide by zero errors. And to deal with those divide by zero errors, in some cases, when it cancels out, you end up with a hole in the graph. If it doesn't reduce out, then you're still going to have a divide by zero error in your final form. Well, that's when you've got a vertical asymptote, something that will not be defined for the function. It can't go through there. It's like a line drawn down, you shall not pass, and nothing goes past it. We also have talked about horizontal asymptotes, and these are the left to right asymptotes that usually are going to tell the function don't cross, but every once in a while you'll notice that one crosses, and that's okay. It's more of a suggestion in some parts of the graph. We'll talk more about that later when we actually start sketching out these graphs. So today, I really want you to work on identifying horizontal asymptotes, vertical asymptotes, and holes in all of the graphs in your practice and homework. And in the next video, we'll start adding more detail to our graph.